Hello everybody, welcome to Lecture 12. We're going to finish off Chapter 10 and start on Chapter 11. Okay, so Chapter 10 is all about the sun. Let's keep going. So how does the energy from the fusion reactions at the core of the sun get out of the sun to us? Well, first of all, energy gradually leaks out of this radiation zone by randomly bouncing around, hitting other atoms, right? So these photons that are made in the core, right? Those gamma ray photons, right? This radiation is going to hit other atoms as it makes its way out of the sun. And in fact, it takes thousands of years for it to make it from the core to the surface. And light travels only slightly better in the sun than it does through rock. So it takes a very, very, very long time because the sun is very dense. Okay, so this radiative transfer that happens right between in the radiative zone from the core to where convection takes over takes a very long time. Okay, and then as that radiation is heating the surface or heating the convection zone, you get bubbling, right? It's just like boiling. And you might have even seen in some of the videos we showed you showing the sun, it literally looks like boiling, right? It looks like it's boiling. It is. Okay, so this convection can take the hot plasma, it says gas here, but really it's plasma, to this from hotter to cooler to the surface, and then and it goes back down again, right? That's what convection does. Okay, these bright blobs on the photosphere show where the hot gas is reaching the surface. So there's a hot bubble of gas has come up, reached the surface. It's the bright spots. It cools because it's reaching the surface, and then it sort of falls back down again, gets more heat, comes back up again. It's exact same process as happens in your water pot where you're boiling water for tea or something. Okay, so how do we know what's happening inside the sun? Well, we make mathematical models and we observe solar vibrations. That's very important. So I'm going to show you a little video, but basically by watching the solar vibrations, and you can see that kind of in this picture here, this is meant to show you sort of higher vibrations, lower vibrations, we can tell a lot about what's happening inside the sun. And then the last thing is by observing solar neutrinos. And this is one of the big things that is a big verification of the fact that the fusion is powering the sun. And I'll talk about that in a second, but let's look at a video.
You wouldn't think you could see a sound or photograph a speed, but those are just two of the ways scientists are building up a picture of how our sun works on the inside. Deep within the sun, in the swirling cauldron of hot plasma called the convection zone, there are bubbles, rather like the ones in boiling water. And like those water bubbles, the ones in the sun create a noise. As they get to the surface, these bubbles of sound squeeze the plasma so it gets brighter in places and at the same time moves upwards. And by measuring that upward and downward movement, the instruments aboard the SOHO spacecraft have enabled scientists to look for the very first time into the depths of a star. These changes, which are incredibly small relative to the vastness of the sun, are as hard to measure as the track of a snail crawling across its surface would be. We could never hear the sounds the sun makes by ordinary means, not just because it's 150 million kilometers from Earth, or because space is a vacuum and sound doesn't travel through a vacuum. The problem is that our star has a very, very deep voice and sings with a very slow rhythm. The sounds ring at a very low frequency, once every 5 minutes. But by recording the natural sound and accelerating it 42,000 times, SOHO has compressed 40 days of recordings into a few seconds. And this is the actual song of the sun.
Okay, so this is all about the field of helioseismology. Remember, on Earth, seismology is the study of earthquakes. That's the sort of shaking of the Earth. Same idea, but you're now looking at the sun. And so that those vibrations that are caused by all the roiling and boiling of the sun can be observed, and we learn a lot from that. Okay. So this, again, the patterns and vibration tell us a lot about what the sun is like inside. And then we use that data to verify mathematical models of the solar interior. And you can see here that the model is the dashed line, kind of deviates a little bit here near the core. But in the radiation zone or the convection zone, it matches very well with real data. So this is how we try to understand the structure of the sun in detail. Okay, now remember, not only do we have a helium-4 nucleus produced in this fusion of 4 protons, etc., but we have these things called neutrinos. So if we could detect these neutrinos, this would be a good verification that this reaction is what's really happening in the core of the sun. Now, neutrinos caused by during fusion fly directly through the sun. Neutrinos are these really interesting little particles that have a very, 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 very tiny mass, if any mass at all. They travel extremely close to the speed of light, and they do not care about matter in general. So they just pass right through the sun, and we have to build really sophisticated experiments to detect them. So this is the Sudbury Neutrino Detector that's located about at 1.2 miles underground. And the reason it's underground is to get rid of interference that might confuse scientists about whether they saw a neutrino or something else. And these neutrinos, trillions of them are passing through your body every second because they are, they don't really care about matter. So you're basically, they're just passing through your body. They're not doing anything to you, but trillions are passing through you every second. And the most recent observations of neutrinos have found the right number, so the predicted number, although some have changed form. So there's 3 types of neutrinos. You don't really need to know that, but 3 types of neutrinos, and we expect a certain type from the sun, and then what happens is they sort of change form as they get here, but before they get here. It's really interesting, but it is definitely a verification that nuclear fusion is what powers the sun. Okay, let's try a question. Pause your video.